right, excellent. I am Justin, and I am here to talk about testing microservices in Node.js. So, who am I, you rightly ask? That is me, or at least a drawing of me, and I am a full-stack developer with more than a decade of experience building web applications, designing, developing, and APIs in all kinds of different languages. Currently, I'm at Capital One, where I manage and lead a couple teams that are building a brand new product from the ground up. So, new Angular web app, new shiny API service is built entirely with microservices on the back end. And before joining Capital One, I was at NPR, where I was the lead dev for npr.org, did a lot of work with React and Redux, podcasts, and other sort of public media-oriented kinds of things. If you want to find me on the internets, you can find me at Justin Bach on GitHub, Twitter, and all the usual places. But enough about me. Let's talk a little bit about Capital One. So as you likely know, Capital One is much more than a financial institution. Really, it's a tech company that happens to specialize in building various financial products and services. And underlying all of the products and services that Capital One offers is a tremendous amount of technology and infrastructure, including hundreds of APIs that are designed for both internal and for external consumption. This right here is developer.capitalone.com, which is the developer portal that Capital One captures all its externally facing APIs and talks about open source contributions and things like that. Definitely worth checking out. But internally, Capital One as a company places a huge cultural premium on engineering excellence and both encourages and requires adherence to industry best practices, which, as you know, are constantly themselves changing. So it's a pretty exciting place to be technically. In that vein, Capital One is adopting microservices at an astonishing speed. We have a lot of support for microservice architecture in general, from leadership, from executives, and we have thousands of microservices in production. We're adding new ones every day. And this talk is based on my experiences leading a team that built a microservice-backed API platform that's in use at Capital One. And of course, any mention of Capital One would be incomplete without my saying that we are hiring. So if you're looking for the opportunity to work for one of the companies that has made Fortune's 100 company list that's best to work for 12 years running, please talk to me on the internet, send me an email, reach out to the folks at the booth there, and they'll be happy to make sure we get you in touch with the right people. Okay, so what can you expect from this talk? We're going to start off with a high-level view of testing, including what we test, why we test, what sort of strategies we use, and this is going to be in a completely technology-agnostic kind of way. From there, we're going to move on to an overview of microservice architecture. Now, despite being a pretty hot buzzword, microservices means a lot of different things to a lot of different people. And this portion of the talk is designed to get us aligned on the same page so that when we actually come to the third part, how do we test microservices in Node.js, we have some coherent and shared understanding of what it actually means in the context of this conversation. And it's in that last section that we'll talk about some more pragmatic recommendations, bring in specific tools and approaches that you can use when testing your microservices-oriented platform. So that's what you can expect. Let's jump right in. So when I'm talking about something like testing, some big, abstract, kind of thorny topic, I like to motivate it with a kind of illustrative sort of example. So if you wouldn't mind indulging me for a little while here, I'd like to invite you to join me on a bit of a thought experiment. So imagine that you are a software engineer, and that's you, right out of college, and you've just taken a job at Awesome Webco, which is a web development agency. You're super psyched. Awesome Webco has lots of high-profile clients, and you can't wait to get to work working with any of them. So one of your first projects with Awesome Webco consists of adding new features to this legacy web application that your company has been maintaining for year after year. And the way that this works is that every year the client comes to you and says, hey, we need these new features added to this application. And you say, cool. And then Awesome Webco says, hey, we've got this new developer. He or she is the perfect person for the job. Let's get them right on it. And so being the bright-eyed and bushy-tailed developer that you are, you build out these new features in record time. And along the way, because you've got the vision, you're drinking the Kool-Aid, you're going to clean up all this code that you encounter that needs to be refactored, so you're changing all kinds of stuff. And everything is really good until the client comes along and starts actually testing things in the QA environment. And the good news is that the stuff you were supposed to build, those new features, really work well and exactly as advertised. But the bad news is that all of the legacy stuff is totally broken. And this comes as some surprise to you. So what happens now? Well, you have to back out all the changes that you made. Fortunately, you were at least using version control, so you got that to fall back on. But it's a pretty soul-crushing experience because you thought you were doing all this great work and cleaning up all this code, when in reality, you were really costing the company a lot of time, costing yourself some emotional energy and physical exhaustion, and the client has lost some of their faith in Awesome Webco, and you are exhausted. So this was not entirely a hypothetical experience. I, for one, have actually been through this exact scenario before. And just out of curiosity, how many of you have ever had to maintain something that didn't have adequate test coverage? All right, that's a lot of hands. We should start a support group. So testing would have helped a lot in this situation. But how, you ask? So one properly written test should at least validate that the thing that we're building functions as expected, and that the new features that we add don't break existing functionality. That's mistake number one that was made earlier. Number two, a good test suite should empower us to be good developers, to do that refactoring, and to really try to clean up things as we encounter them instead of saying, no, don't touch that code, it works, and nobody understands why. And number three, properly written tests serve both to improve the architectural quality of the code under test and to document that architecture and that code and that expectation so that when future generations of legacy code developers come along, they're not stuck in the situation that I was and that apparently all of you were as well. Now, everything I've said is very much a developer-oriented view of why testing is good, but I really don't want us to lose sight of the importance of users in this conversation. Because ultimately, the goal that all of us have at the end of the day is to deliver really high-quality, consistent experiences to users as quickly as possible. And having really compelling, strong automated testing is a very good way of at least mitigating the risk that the changes we make, the new features that we add, are not going to break that experience and allow us to tighten that cycle of releasing code and monitoring code and seeing how users react, responding to changes in their behavior, developing new code, testing that code and releasing it. In that scenario that I was talking about earlier, there was a really big smell, and that's that the client was doing testing in QA of things that we were developing. And that is just not tenable for any kind of development at scale and any kind of rapid release cadence. So that is a little bit about why we like to test code. From here, I'd like to dive into some of the types of tests that you may encounter in your career as a software developer, beginning with the classical testing taxonomy, which I'm sure a lot of you have encountered. I like to think of this as the trio of unit, integration, and functional tests. So let's talk about each of those a little bit in detail. So unit tests, what are they? They are tests that typically check the functionality of code at the level of interfaces exposed by a particular class or a module. So if a class exposes a particular method, we're going to have unit tests that check the behavior of every single code path through that method to make sure it functions as advertised. And traditionally speaking, unit tests are developed in complete isolation from any external dependencies. So that means if your method talks to a database, you mock that. If it talks to anything over the network, you mock that connection. If it generates a random number, you probably need to mock that as well. And you use some tool like sign-on or something like that to handle your mocks. As mentioned, you want to make sure you execute every single path that a unit test can take, that a code can take when you're writing unit tests to ensure maximal coverage. And this is often done through the practice of test-driven development or red-green refactor, where you write tests for functionality that doesn't yet exist, write code to implement that functionality, and watch the test pass. And of course, here is a picture of a Lego. This is the fundamental unit of the universe, so it seemed like an apt visual metaphor for what we're trying to capture here. So a good unit test is more than just assurance of correct functionality. It's also a good source of bug reporting. So the test suite failed. Great, now what? How do I fix it? So specifically, a good unit test should tell you what component was being tested. Was it a class, module? What was the function? What's the behavior of the test that we expect to see? So was this a happy path? Was this a sad path? Was this some medium path? I don't know. What were the actual results observed during this test? What were the expected results? And how can we reproduce this apparent failure? And a well-written unit test will give you all of these things. So I'd be remiss if I didn't mention Eric Elliott, who has a lot of great blog posts about unit testing and testing more generally in JavaScript. Would definitely recommend checking them out. And I will post these slides, so you'll be able to find the links later on. OK, so that's unit testing. Now, moving on to integration testing. They're the next step up the ladder, and they test that the units of code that we've already tested exhaustively, remember, actually integrate together correctly. So in contrast with unit tests, with integration tests, you typically have little to no mocking, which means you're hitting databases, you're hitting file systems, you're making requests over the network. And as such, you also don't usually exhaust every single code path the way you do in a unit test. So the level of coverage typically goes down with an integration test. The assumption is that you have confidence in the suite of conditions from the unit test that you're writing. Integration tests are generally a little bit coarser in that regard. And so an integration test of Legos would make sure that individual Legos, which have been, remember, tested separately, actually fit together as advertised. So that's integration testing. One more step up the ladder is functional tests, which are sometimes called end-to-end or smoke tests, and they tend to evaluate the functionality of whatever it is you're building from the perspective of the user, as opposed to from the perspective of the systems architect or the author of a particular component. And generally speaking, this will involve testing your application through a web interface or whatever the UI is that your application happens to actually expose. You can run these in production, perhaps after deployments, and call them smoke tests as a way of making sure that your deployment actually went successfully. And in general, like integration tests, functional tests tend to be less exhaustive, less full in terms of coverage, and run later in your deployment pipeline. And we'll talk more about deployment pipelines in a bit. So in the world of Legos here, a functional test might ensure that the thing that all the Legos that came in this box come together to represent actually matches the user's expectations of what was depicted on the box. So that's the classical taxonomy of test types. But there's other ways of talking about tests as well, and I'd like to spend a few moments thinking about those. So Google has this notion of small, medium, and large tests that some of you may have seen before. And I find that this is pretty interesting because while if you sort of squint your eyes, it looks like small tests are unit tests, and medium tests are integration tests, and large tests are functional tests, there's a lot of ambiguity around what exactly a unit test or an integration test or a functional test consists of when you go to have a conversation with another developer about it in a particular context. So what Google did is they identified a bunch of different axes. So network access and database, file system access, sleep, system properties. How long does your test suite take to run? And they apply those as criteria when determining what kind of tests you actually have. And what this empowers Google to do is have conversations that make sense across the entire company, which uses a ton of different languages, test paradigms, stacks, CI pipelines, all kinds of different things, while still maintaining some degree of coherence about what a test type consists of. So this is kind of an interesting way of solving that problem. One more thing I'd like to go into a little bit is the distinction between white box tests and black box tests. So who has heard of these terms before? All right, cool. Seeing some hands. So in general, with a white box test, you assume knowledge of the implementation of the code that you're actually testing. Whereas with a black box test, you make no such assumptions, and you test only according to the specification of the thing that you're trying to test. And so there's a couple things that I want to talk about here. The first is that if you're using mocks, it kind of automatically classifies your test as white box. Because in order to properly configure and set up a mock, you need to know how the code under test is interacting with that mock, meaning you need to be able to set up the mock and have all of your code that does assertions on the mock and things like that to validate correct behavior. And that means, in general, that white box tests tend to be a lot more tightly integrated with the code under test than black box tests. And what that often means as a follow-on is that if you change the implementation of code under test, even if the behavior is the same from the perspective of the user, you need to rewrite the tests. And that reduces your degree of confidence that the changes you made are actually correct. Because you're updating the tests, as you're updating the code, you've lost some degree of confidence in your test harness because you're making these changes in parallel. If you don't touch the tests, you know that the observed behavior is the same. Your refactor is safe. If you do touch the tests, you might have screwed that part up. And I've certainly been bitten by that in the past. So in general, black box tests are more resilient to refactoring than white box tests because we're not changing the tests. One other point is that devs often think about unit tests as kind of like inherently white box and other types of tests as more black box. And there is some degree of truth to that, but it certainly doesn't have to always be the case. So if you take, for example, pure functions, which have a parameter set, and then based on those parameters, deterministically return some value without interaction with any external systems, without any kinds of side effects like logging or API calls or random number generation or network access, you can actually test those in a black box manner pretty confidently and pretty well. And in fact, if your application or your platform has a bit of thorny business logic that you want to make sure is really well understood and well tested, there's good value in trying to make sure that's a pure function so that it's more resilient to refactoring than anything that is constantly hitting the database and going over the network and things like that. So that's a whirlwind tour of a couple of ideas about testing. Now I'd like to shift gears a little bit and talk about microservices. And that means, you guessed it, it's time for another thought experiment. So imagine that you are building an app, and this is going to be the next big thing. Specifically, this app is going to let people with dogs share the responsibility of walking them. So this is going to be kind of like carpooling, but for dogs. So I don't know, let's call it dog pool. And this is cool. We have this client app, and it's going to be built in Angular or Vue or React or who knows what, or maybe it's a native app. But it's going to need a backend of some kind, right? Because we need to have a way of storing and retrieving data about these dogs and users and schedules and dog ownership. And we need to have some backend business logic for working with all that stuff. But what does this look like? Well, this is a JavaScript conference, so I'm going to go out on a limb and say that it's probably going to be a Node app. We may as well use something like Express for our framework because it's mature, it's widely supported, well understood. We're going to need to store relational data of some kind because we have all this data about users and dogs and schedules, so let's use Postgres for that because it's cool. We're going to want our API calls to be fast, so we're probably going to need some caching. Redis seems like a good bet. And maybe we're going to need to do something with queuing or message brokering or asynchronicity, and let's just leverage Kafka for that purpose. Maybe it'll even be event sourced at some way down the road, but I don't want to get too far ahead of ourselves. All right, so we've got this whole stack. It's cool, it's powering our client app, and it's actually working pretty well. The users are powering in. Or they're pouring in because our API is doing such a good job of powering our platform. Everybody, it turns out, wants to walk other people's dogs. Who knew? So we've got a winner on our hands. Tech industry loves us, we get funded, we start hiring employees, and the product grows and grows and grows. And with that, in addition to our core offering of helping users schedule dog walks, we also branch into other things like cat cafes and various other esoterica related to the pet renting industry. Along the way, we start supporting multiple clients. So we had this first client we wrote, and maybe we have a tablet client as well. And then our business partners start thinking, hey, wouldn't it be cool if we could engage with some other companies to have them unleash the power of the Dogpool platform? So now we have this business partner integration API, all this really cool stuff that's happening. And as the success story is unfolding, we noticed that this backend that was initially this humble little Express app is starting to take on a lot of responsibilities. So those are including, but not limited to, dealing with user management, handling pet inventory, handling walk scheduling data and logic, producing business reports and analytics, sending notifications via SMS and push notifications and emails and things like that, supporting APIs for our different clients, supporting APIs for our different business partnerships, and maybe there's even public APIs too, so that enterprise and developers like you and I can find new and innovative ways to do stuff with dogs and dog walking schedules. But what this means is that we're having a lot of trouble maintaining this application because anytime we want to make a change to, for example, the database, we have no idea what parts of our app are using a particular field or column. So this is requiring a ton of testing, and there's a lot of knock-on effects from deployments that have gone sideways based on unanticipated consequences. It's also getting really hard to hire new engineers because as you start ramping them up, they have to understand the system as a whole, and this is just not tenable. And as the dog sharing marketplace grows increasingly more and more competitive, Dogpool is quickly losing its edge. And that is because we have built a bloated, unmaintainable monolith. And it can have a lot of drawbacks, including those I've already discussed. Now, side note, not all monoliths are bad, and they can be very well engineered, and they can be very well modularized, but I've been in this situation too many times to know that that is not always what happens. So too often you do end up with the sorts of situations that I've already described, in which you have tight coupling between unrelated domains. Coordination across teams becomes a real headache, and merge conflicts abound. You have massive deployments that are necessary even for very small changes to features. You have technological lock-in. It gets very difficult to break out of the tech stack that you adopted initially. And there's a very steep learning curve for new developers, as I mentioned. So what can we do about it? One possible solution here is to adopt microservices. And in this context, what we mean by microservices are small, independently deployable, tightly scoped services that handle a single, well-defined business capability. They tend to work together using standard network protocols to service requests to the system as a whole. And there's not really any hard and fast rule about how big these microservices should be, but one general rule of thumb is they should be small enough to be rewritable by a dev or maybe a couple of devs in a cycle or two. So what might our platform look like if we adopted microservice architecture? So instead of having one single Express app with lots of dependencies and various types of infrastructure, we now have broken down our business domain into a number of different contexts, each of which is owned by a microservice. So in this case, we have separate services for user management, for dog inventory, for scheduling walks, for notifications, and for analytics and business reports. Each of these services is its own fully fledged application with its own code, its own backing infrastructure, and the services communicate with one another via standard network protocols. So in this case, I'm assuming an HTTP API that's used for service-to-service communication. There are, of course, alternatives to that. So you can use binary formats like protocol buffers and gRPC. You can also have asynchronous communication models that rely more on shared pub/sub and that kind of approach. But for purposes of this talk, sticking with classic HTTP API-driven approach to services. So what does this buy us? Well, the first is that we now have pretty cleanly separated concerns, assuming that we got our microservice boundaries correct, which is an art into itself. If you do this wrong, you'll end up with all kinds of shared concerns, and it'll be even worse to maintain than a monolith. But that's an entirely different topic. We have lots of small applications that can be tested independently and then deployed independently, so we can deploy a lot more rapidly with much less pomp and circumstance. And it also becomes much easier for new engineers to understand each one of these services in isolation. Technological heterogeneity means that we can cheaply experiment with new technologies and pick the right tool for the job. So if you have a service that's really focused on a lot of in-memory computations, you might pick one language for that. If you have another service that's mostly making API calls and is I/O bound, so you pick something that makes a little bit more sense there. And lastly, if you adopt this correctly, microservices should generally lead to the creation of a much more resilient system, because failure is now something you have to account for in every single transaction that occurs between microservices. This means you have to adopt patterns like circuit breaking and handling situations when your downstream and upstream services just aren't available. So Martin Fowler has written at length about these various trade-offs, advantages, and disadvantages. And again, this blog post is a great place to go to read more about it. So a lot of organizations see that list, and they get really amped about the notion of using microservices to solve all their problems. But the bad news is that it comes with a fair amount of infrastructural overhead. And if you adopt a microservice architecture before you're ready for it, that can put you in a world of hurt. So you need to have a pretty sophisticated DevOps-oriented culture for things to go right here. There's a couple different tools that are helpful for that, and I'll talk about those in turn. So one is containerization technologies like Docker. I assume that a lot of you all are using Docker in your day-to-day jobs these days, but it's hugely helpful when you're building something with microservices because, well, there's a couple reasons. One is that you have this model of a single process per container in Docker that works pretty well with a single responsibility per microservice in microservices architecture. Another is that it tends to lend itself to a build once, run anywhere kind of approach to setting up your application. So you can build your image in one place, you can deploy it to integration testing, deploy it to QA, deploy it to production without worrying about differences in the build job that may vary between those environments. And using Docker also makes it much easier for developers that are trying to work on several microservices at once to actually spin them all up locally and see the overall gestalt, sort of the shape of the transactions that span multiple services, using things like Docker Compose or Minikube, other options. So Docker's great. Once you're using Docker to write your services, using something like Kubernetes becomes really advantageous for deploying them and managing them. It makes it very easy to deploy a specified version of a service in a declarative kind of fashion to different environments. This version's in QA, this version's in production. And you can also actually overlay different logical environments inside a single physical cluster, which is really a great cost-saving technique. So you can have a single cluster run on a set of EC2s that comprises integration testing, QA, probably not production, you probably want to separate that, but do your thing. It's just a really nice way of being able to have a separation between logical and physical environments. And Kubernetes also helps to mitigate a lot of other microservice-related headaches. So there's all these cross-cutting concerns like health check monitoring and auto-scaling and service discovery, analytics, logging, and Kubernetes does a great job of helping to wrangle the complexity that increases to when you adopt microservices. And of course, it's probably barely warrants mentioned in 2018, but please use some sort of cloud-based service. Having APIs to provision and destroy your environments makes all of this much easier to manage rather than trying to actually run all of your own infrastructure. OK, so that's a little bit about infrastructure. There's also another critical component to having a well-cared-for microservices system, and that is to use a CI/CD pipeline. And really, that doesn't it's not limited to microservices. Anybody developing any software in 2018 should be using CI/CD to manage their code as it makes its way from dev to production. So to do so, you need some sort of task runner. So Jenkins is a choice that we use a lot at Capital One, but there's plenty of other options as well. And Jenkins can do anything from setting up infrastructure to running unit tests to running linting and integrating with other things like GitHub to check PRs and let you know that they're either ready to merge or not. Taking a step up in abstraction, you get to tools like Spinnaker from Netflix, which can be used to create easily visualizable and managed pipelines. So when I say pipeline, I mean something like this, which helps tracking code as it makes its way from dev to QA to integration testing to pre-prod to prod. And there's usually some degree of testing that happens along the course of the pipeline that rolls out here. And as your pipeline marches closer to production, the nature of your testing becomes typically less granular, it becomes a little bit more coarse-grained, and the level of coverage typically goes down as well. And both Jenkins and Spinnaker manage their jobs and their pipelines as code, which makes it really easy to version them and track them in GitHub and do PRs and have your standard ordinary code review practices in place for dealing with these things. One other thing I'd like to touch upon here is this architectural notion of backends for frontends. Is this something you all are familiar with? OK, a couple of hands. So one common problem that people run into when they start adopting microservices is that they are like, oh, I'm going to have all these services that do all these things. But then I also have external clients that are going to depend on some of these things that these services are doing. So you end up with services that are like half beholden to your little microservices world, and then services that are like also kind of half beholden to external clients, and it becomes really difficult to reason about who's doing what, why, and when. And so in Backends for frontends, what you do is you spin up dedicated services for every single external API that your platform as a whole needs to support. And this has a lot of advantages. The first is that it means that those public-facing services can deal with all the details of managing the requests and the responses to particular clients, and shield all of the implementation level services from having to worry about all that stuff. So in some ways, this is a lot like the facade pattern in object-oriented programming, where we're essentially exposing some subset of the full suite of capabilities that our platform offers based on the needs of the client. And we're maybe changing the nature of that exposed subset of capabilities in a way that the client will understand. It helps to separate those concerns pretty nicely. This is not a new pattern. So the term Backends for frontends was coined by Phil Calzado from SoundCloud. A guy named Dan Jacobson, who worked at NPR and is also a VP at Netflix, called the public-facing layer here the experience APIs, and the backend layer the ephemeral APIs. And I quite like that because it really brings home the notion that the experience APIs are powering the user experience, and the ephemeral APIs are all about reusability and disposability and experimentation and not relying on from one day to the next. So that's kind of how you want to think about your services, both from an API interface design standpoint and from an implementation standpoint. And Etsy does something similar as well. Etsy has a notion of component and composite APIs. So in their world, the component APIs are the ones that implement particular business capabilities on the back end. The composite APIs assemble those components to fit the needs of every external client that they have to service. OK, so with that background established, we can finally start the talk, which is all about testing microservices in Node.js. So hi, I'm Justin. I'm here to talk about testing microservices in Node.js. OK, so in order to test anything, we need to have an example to test. So the example that I conjured up is based in our dog pool app, which I hope you all remember from a couple minutes ago. And this particular API request is made to get dogs. So we can make a couple assumptions here. One is that this request is going to be accompanied by some sort of authentication, so perhaps an OAuth2 bearer token. And we're also assuming some sort of three-legged OAuth. So we're going to assume that we can infer on the basis of this bearer token the context of the user that is making the request. So the behavior of this endpoint is to return all the dogs that belong to the currently logged in user. And here's a sample response. So we assume there's some dog whose name is Biscuit. We have a nice, easy-to-read UID4 that identifies Biscuit uniquely in probably the known universe. And then we have some most assuredly adorable photo of Biscuit as well, and possibly more dogs if our logged-in user has more dogs, but the slide is not big enough for us to find out. So what might the implementation of this API capability look like from a microservices standpoint? This is one possible way we might implement that. So again, this is using the backends for frontends paradigm that I discussed moments ago. We have some client, our native app, that makes a request to get dogs. The public API sees that request and says, oh, I need to orchestrate some calls in order to formulate the correct response for this client. So I'm going to go first to the auth service, where I'm going to pass along the bearer token, validate this request, and then get back a user ID. And then I'm going to go to the dog service, and I'm going to make a request to get all dogs, but filtered by this particular user ID. And then I'm going to do whatever I need to do to format that dog data in a way that this particular client expects, and I'll send it back. And I will, as a caveat, just point out that this is probably not a totally realistic example because it's very likely you won't have your own microservice that's handling things like OAuth2-based session hydration. You probably have some off-the-shelf API gateway kind of solution that'll be doing that for you. But the general principle holds for how you might have a distributed microservices call. So that's why I chose it for this talk. So this is kind of a friendly, hand-wavy way of depicting that particular interaction. A more structured way of doing this is using a sequence diagram. So this captures exactly the same flow, but in a good bit more detail, and can be very helpful in documenting exactly how key transactions work in the context of your microservice-based application. So again, we have a call from the API client that goes to get dogs from the public API. Public API is going to post to sessions validate, passing along whatever authentication data is needed, gets back a user ID, or perhaps some sort of failure mode, in which case public API is going to send some 4xx kind of response. If all goes well, though, the public API is going to go back to dogs and say, hey, get me the dogs for this user ID. Dogs comes back with dog data. The dog data is formatted and then returned to the API client. And I should also mention, I didn't realize how confusing dog data would be in the context of Datadog. So please try to keep those terms straight as we proceed with this talk. So this is the route under test. But how do we test this? Bearing in mind what we talked about earlier in this presentation about the different layers of testing. So let's start by talking about unit tests for a little while. So to do this, we need to get up close and personal with the dog service. And every one of the services that we looked at, so public API and auth and dogs, is going to have its own accompanying suite of unit tests. But we're going to focus on dogs for now as an example. So what do we know about this service? We have a pretty good idea of the technology that was used to create it. And we also know a little bit about its behavior. Namely, we know that it can be used to get back some dogs. So let's dive in a little bit deeper. We probably have some dog model. And that dog model is probably good at finding dogs by user ID. So we're going to conjecture the existence of this particular method. And let's imagine that this is the method that we're curious about for purposes of writing our unit tests. So here's one possible implementation of this method. This is not anything like production code. It's an example, but I think it serves our case here. So we have find by user ID. And it's an async method, so it's going to return a promise. And it's going to take a couple of parameters, so like a DB instance, and then the user ID. And it's going to do a little bit of error handling, so check to make sure that the user ID is defined and throw an error. Probably should check for the database too, but the slide's, again, not big enough for us to do that. And then once it knows the user ID is good, it's going to run some SQL, properly escaping things to prevent SQL injection and all that good stuff, and then return the result of that particular operation. So this is the method that we want to test. What might a test of this method look like? Here's one possible example. So this is checking the happy path through the test. And as such, it is describing find by user ID and saying it should return the dogs that belong to the user. That is exactly what is advertised. So in general, this is not specific to unit tests. Every test should have 3 distinct phases: arrange, act, and assert. So arrange sets up preconditions for the test. Act actually exercises the code under test. And assert makes some assertions about what you expect the results of the test to be. So in this case, when we're arranging, we're inserting some test data. Maybe we're setting up some mocks, not entirely clear. Then we're going to run the code under test, so dog.findByUserID. And then we are going to check to make sure the actual data that we got back equals the data that we expected to see. So I kind of glossed over the mockness or non-mockness of this test. And that was intentional, because it's not really clear what's going on. Insert test data could be fixing up the DB object that's passed to it, maybe mocking it out somehow. Or it could be actually making live insertions into a database. And this is probably one of the most controversial things I'll say in this talk, but we found in our experience that it's frequently worthwhile to actually run unit tests in models against a live running database instance. And the main reason for that is that when you run a test with mocks, what you're testing is that the SQL that your model method emits is the SQL that you expected it to emit. And when you run it against a live database, what you're checking is that the behavior of that query is correct. And more than once, we have found that the query matched what we expected, but the behavior of the query was completely wrong. So this gets very much back to the notion of white box versus black box tests that I discussed a little bit earlier. There's a lot of different ways of writing a SQL query that's going to generate the same results. And if you run this against a live database, you'll actually be able to refactor your query in a way that is still semantically correct and guarantee that your running tests and your passing tests constitute confidence that the behavior is unchanged. Whereas if you change the query, you have to change the white box-oriented unit test. That loses some degree of confidence in your code behaving as intended. So there's a couple of arguments that are classically made against this kind of approach. One is that it's a pain to set up a new database instance every time you have to run a test. And the other is that my test suite is going to run really slowly if I run all my tests against a live instance. And what we found is that using Docker, and specifically Docker and Compose, to spin up a new instance of MySQL or Postgres or whatever right next to the code that you're testing is really cheap and really fast. And that if you're running and writing microservices, the number of tests that you have of this nature should not be so great that the cost that you pay by having real requests made against the database is actually that punitive. If it is, maybe it's time to rethink the scope of that service, split things down a little bit. So again, your mileage may vary. We have found this to more than once be a very worthwhile trade-off, but you can just take that and do with it what you will. OK, so in general, unit tests exhaustively test individual methods, one code path at a time. So we would need additional tests for that method, get dogs by user ID, to test errors and things like that. They live alongside the code under test, so in the same repo. We run them on every commit and on every pull request. So on every commit, we do this using pre-commit hooks that we all use locally. And then on pull request, we handle that through Jenkins integrations with GitHub, which I touched upon a little bit earlier. And in general, unit tests tend to be quite a bit more white box. than other tests, with the caveats of the prior discussion that I brought up being brought to bear here. So what kind of tools do we use for this? We need some sort of testing framework, which is going to actually run our tests and provide the means of framing them. So if we have Mocha, that encompasses using describe, it, things like that, but there are other options. We need some sort of assertion library to make assertions about the behavior of our test. So there's different TDD, BDD style things. You can pick and choose what you like. You may want to have some sort of mocking plugin, should you choose to go the mocking route, and sign-on is a popular choice for that in the Node world. And then you also want some kind of coverage reporter. So Istanbul, NYC are good options for this to make sure that you're actually exercising as much of your code as possible and really shooting for 100% test coverage. So that largely covers unit testing. I'd like to now move one layer up the testing ladder here and talk a little bit about service integration tests. So at the unit level, we're checking on the behavior of a particular method in a particular module. At the service level, what we're checking to make sure is that an endpoint that a microservice exposes actually functions as expected. So what can we say about the nature of these tests? Well, in general, we want to exercise the full request cycle at the microservice level when we're writing service level integration tests. And that means we want to validate the routing of the request, so we want to make sure all the routes work. We want to make sure that all of our middlewares are hooked up and configured properly. Just like unit tests, we want to run this on every commit and on every pull requests. And with service level integration tests, we tend to take a kind of gray box approach, so halfway between white and black. And the idea here, the guidance, is that everything should be black box with respect to internal dependencies. So if your microservice depends on a database, run that locally. If your microservice depends on some downstream service that's outside the purview of your service, mock that out. And the idea there is that you don't want your local service integration test to fail just because some downstream test isn't available on your local machine or is having its own problems, that kind of thing. In terms of tooling, we want to use all the tools that we've already become familiar with when doing our unit testing. So this is the framework, the assertion library, the mocking tool, all that kind of stuff. And we also want to introduce supertest. So people here are aware of supertest? Used it before? Fewer hands than I was hoping to see. OK, so supertest is great. It's a lot like a super agent, which is a library for making requests in Node. But with supertest, what you do is you pass in an instance of a running Node app. So it could be what you get back from calling Express, for example. And you can make requests against that instance and then verify things about the nature of the response that you get. So what that might look like for a service integration test is the following. We are describing a particular endpoint. So in this case, we want to get dogs, passing in a particular user ID with which we want to filter the results. And the behavior is it should return 200 and the correct dogs. We do not want to see the incorrect dogs. So to actually run the test, we make a request. We're using async and await. So we await the request. And then I missed an async keyword up there. Oh, well. We make the request. We pass in the app instance, which we're going to be creating again to use with supertest. So in this case, request is aliased to supertest. We get the response back, and then we change some assertions onto it, like the expectation that we get a 200 back. And then we say that we expect the actual response to be the response that we expected. That is, to be sure that we actually got the correct dogs back. So one question that we often get about how exhaustive these tests should be, I like to answer the following way. Because with unit tests, remember, we want to test all the code. We want to test all the paths. With service-level integration tests, our goal is mainly to make sure that our routes are functioning correctly and that all of our middleware are properly hooked up and configured. So basically what that means is you need to have enough tests to give you confidence that every middleware is in the stack and working as expected. So a more concrete example of that might be if you have an error handling middleware, say, you want to be sure that you have a service integration test that triggers an error condition and that the response you get back is formatted according to the behavior of that error handling middleware. More generally, that error handling middleware probably has its own accompanying suite of unit tests, so you don't need to test every single path in that middleware, but you want to at least make sure it's plugged into the stack correctly and working properly. So that is how we handle service integration tests. Taking one more step up of the hierarchy of abstraction, we arrive at platform integration tests. And remember, with unit tests, we're checking a particular function. With service integration tests, we're checking the behavior of an individual service. With platform integration tests, we're actually checking the behavior of our API product as a whole from the perspective of an outside observer. So in this case, we're making requests against the public API layer. That's the backend for front end, to make sure that everything is functioning as expected. And to do that, we actually stand up a Docker container that is the test runner, totally externally from a fully deployed microservice suite in some staging environment. So platform integration tests tend to reside either with the public API repo itself or perhaps in an external repository. There's a good case to be made for having it live with the public API repo because that ensures that you can author new tests as you're adding new functionality, and you can kind of keep those things synced up, which is generally desirable. And then that just means that your external Docker container is a deployment of your public API that's serving only to run integration tests against whatever your deployed environment happens to be for testing. Speaking of which, you need to run this against a full staging environment. So there's sort of a split opinion as to whether it's good to run a full staging environment when you're running a microservices-based architecture. Some companies actually just run everything in production and just roll out versions of a microservice incrementally, divert a little bit of traffic to it with a canary deployment or something, and then roll back if things don't work well. We actually have been using full staging environments for our services, and we have not lived to regret it yet. Also, these integration tests tend to be completely black box with a caveat that it's sometimes acceptable to mock external services. So when I say external services in that context, I mean external to our microservice-based platform as a whole. So recall that when we were talking about service level integration tests, we talked about it being okay to mock requests to other services. When we are talking about platform integration tests, we are mocking requests to services that are external from our particular property, the thing that we're trying to run. And that's because we don't want, again, reliance on external vendors or other APIs that we don't control to make us think that there's something wrong with our stack. There is obviously a need to test integrations with external APIs to make sure that those are working properly as well, but we don't do them in this context. So what tools do we use for this kind of test? Well, we obviously need a framework and an assertion library, and instead of using supertest or anything like that, we actually use a real request library, so like request promise or fetch or super agent, something like that. And if we do choose to mock dependencies on external systems, that's when having a tool like wiremock comes in real handy, because that lets you set up a deployed instance of a server that mocks whatever your external APIs might be. And further, you can actually configure that deployed instance to allow you to verify that calls that you were expecting to see against it were actually made. That's a little bit more white boxy, of course. So here's an example of a platform integration test. We are testing get dogs, and we want it to return the current user's dogs. So note that the semantics have changed there a little bit. Now it's the current user's dogs, which is the behavior of the endpoint to a public API client. When we were testing this behavior at the service level, we were looking for a correct set of dogs filtered by some arbitrary user ID. So this reflects a little bit of a nuance in the semantics of these endpoints. So how do we do this? Well, we set up a reasonable looking request. We configure the method, the host, the headers. So we're actually configuring real authentication here. And we're making a live request using request promise, and then checking to make sure that the response that we get back is actually what we expect it to be. So a couple things here to talk about. One is that this is going to require some sort of test fixture data. And there's a couple different ways of doing that. One way is to have a Jenkins job or something that actually goes through all of your different services and sets up all of the preconditions that are necessary for this call to function correctly and to actually have the right dogs hydrated wherever you expect them to be. That is kind of brittle, because that means that this one job has to be aware of all these different schema and that has to be updated whenever those schema change. It's a lot of maintenance overhead for your system as a whole. So another approach that can be taken here is to actually have the preconditions set up by prior test cases. So in this particular context, that might mean we make some calls to post or put dogs to set up whatever we expect to get back. And that has some implications for things like test isolation. So we haven't talked about test isolation much, but one general principle is that all things being equal, it's good if a test fails because there's something wrong with whatever that test does and not because of something that happened in another test. If you have dependencies across your tests for setting up preconditions for downstream tests, that's a little bit problematic, but maybe that's a worthwhile trade-off because it turns your test suite into more of a black box one. You're no longer aware of the database schema of all of the services that are running on the back end here. You're just making requests against your platform as a whole, and that's, I think, advantageous. Okay, one more type of test, extra credit, and that is the end-to-end test. So in our platform integration tests, we were using some sort of Docker instance to run API-based tests against our public API layer. But in end-to-end testing, we actually use a real client app to make sure the system functions as intended. So this is usually going to be driven by some sort of browser or UI automation tool, so something like Selenium or Nightwatch, Cypress, things like this. So a couple things to say. Note that for this to be effective at all, you really need good unit testing and integration testing before you get to the stage in your deployment pipeline. Because imagine that this test fails. that is an enormous problem space to dive into and figure out what the hell actually went wrong. It could be a bug in the client code, it could be a bug in one of your services, it could be a bug in your public API layer. So it's really important to have things that'll help you cut down that search space. And then if you do discover a failure here, add unit tests at the right level to make sure it doesn't happen again. But regardless of that risk, end-to-end tests can be a really good way of gaining confidence that your deployments are going to go well, or that if you've just deployed some code and you can run this in production, that things are actually working properly. So if I may add one more metaphor to the mix, I like to think of these various types of tests of microservice systems as layers in a cake. At the bottom, you have your unit tests, which serve to make sure that all of your methods exposed by classes and modules are functioning the way that they should. Above that, you have service integration tests, which make sure that your microservices independently are actually upholding their side of the API bargain. And then above that, we have platform integration tests, which check to make sure that the API contract that our entire product exposes to the outside world is actually working as advertised and being correctly fulfilled. And end-to-end tests really are just the icing on the cake. They may seem excessive, but it's really not the same without it, and would highly recommend adding that layer to your cake. So remember that this is just one approach to testing microservices, and every organization has a very different microservices journey. So this is me talking about some things that we've done at Capital One in the course of my team that have worked pretty well. But you may find a solution that better suits whatever your particular microservice configuration looks like. To abuse the metaphor a bit, perhaps you prefer carrot cake or chocolate, or perhaps even cheesecake to red velvet. Who am I to judge? But the most important thing that I will implore you to remember is that testing is important not as an end unto itself, but as a way of helping us to deliver higher quality user experiences more quickly. And I would like to think that regardless of the flavor and the structure of the cake, that is an outcome that we can all support. So thank you.